In the annals of engineering, some structures stand as monuments not just to human ingenuity, but to our humbling failures. They remind us that even the most robust designs are locked in a relentless battle against time, nature, and sometimes, human oversight. Our story begins in a vibrant city, on a bridge that was once a symbol of progress, only to become a tomb for dozens. It's a story of a silent killer, slowly devouring steel, until a moment of catastrophic release. St. Louis, Senegal, a city steeped in history, positioned at the mouth of the Senegal River, needed a lifeline to the mainland. The Faidherbe Bridge, inaugurated in 1897, was precisely that. At 510 meters, spanning 7 impressive sections, it was a marvel of late 19th century engineering. It linked island to shore, commerce to community, standing as a proud testament to an era of industrial ambition. It was designed to endure, to connect, to facilitate the very pulse of life in this bustling West African hub. Though often attributed to the legendary Gustave Eiffel, the Faidherbe Bridge emerged from the workshops of his very own company des Établissements Eiffel. The actual design ingenuity belonged to the triumvirate of Nougieré, Koechlin, and Sater. Their vision delivered a structure that combined robust wrought iron with innovative steel components, including a critical central swing span. This allowed ships to navigate the Senegal River, maintaining the city's vital maritime trade. It was a sophisticated design for its time, embodying the pinnacle of structural engineering principles. For decades, the Faidherbe Bridge served its purpose faithfully. But silently, relentlessly, an unseen enemy was at work. The harsh marine environment of St. Louis, with its corrosive saltwater air and strong winds, began to chip away at the bridge's defenses. Rust, the insidious offspring of oxygen and moisture, was not merely a superficial blemish, it was a structural assailant, compromising the very integrity of the steel and wrought iron components. The bridge was aging, and its environment was unforgiving. As the years turned into decades, engineers and local authorities began to voice concerns. Cracks appeared, joints groaned, and the once proud structure showed increasingly obvious signs of distress. Reports were filed, recommendations made for comprehensive maintenance and structural assessment. These were not whispers in the dark, but explicit warnings, echoing through the administrative corridors. The bridge, like an ailing patient, was exhibiting clear symptoms, begging for intervention before it was too late. Yet, these warnings, critical as they were, often fell on deaf ears. Economic constraints, bureaucratic inertia, and a perceived lack of immediate danger led to a devastating pattern of deferred maintenance. Cost-cutting measures became common practice, prioritizing short-term savings over long-term structural integrity. This wasn't merely neglect, it was a gamble, a dangerous wager against the relentless forces of material degradation. And the stakes, unbeknownst to many, were immeasurably high. At the heart of the impending disaster lay a concept engineers now understand intimately: material fatigue. Unlike a sudden break, fatigue is a cumulative process. Microscopic cracks form under repeated stress, gradually propagating until the material can no longer bear the load. Think of bending a paperclip back and forth. It doesn't break on the first bend, but eventually, it snaps. The Faidherbe Bridge's steel, under decades of traffic vibrations, wind stress, and thermal expansion, was slowly, imperceptibly, succumbing to this silent, destructive force. Investigations would later pinpoint specific vulnerabilities. The bridge's pin connections, crucial joints holding its massive sections together, and its delicate lattice girders were particularly susceptible. These elements, constantly under stress, were made weaker by the pervasive corrosion. Each cycle of load, each gust of wind, each passing vehicle, gnawed away at their remaining strength. The bridge was a chain, and these corroded, fatigued components were its weakest links, teetering on the precipice of failure. The date was June 20, 1964. The time, approximately 4 p.m. A typical afternoon in St. Louis, bustling with activity. A crowded bus, packed with passengers, began its journey across the Faidherbe Bridge. Behind it, a heavy truck followed. The load was not extraordinary for the bridge's original design capacity. But the bridge itself was no longer its original self. It was a skeleton of its former strength, ravaged by years of neglect and the relentless marine environment. The stage was set for an unimaginable tragedy. Suddenly, without warning, the central swing span buckled. A horrifying roar of tearing metal and splintering steel filled the air. The section of the bridge, along with the bus and the truck, plunged into the churning waters of the Senegal River. It was a swift, brutal descent into chaos. Eyewitnesses described screams, the splash, and then an eerie silence as the river swallowed steel and human lives. A lifeline became a death trap. A symbol of connection was violently severed. The immediate aftermath was horrific. Rescuers rushed to the scene, but the swift currents and entangled debris made their efforts agonizingly difficult. The waters yielded a tragic tally: 46 confirmed dead. These were fathers, mothers, children, ordinary people caught in an extraordinary catastrophe. The loss reverberated through St. Louis, a wound etched deep into the community's memory. It was a stark, brutal reminder of the ultimate price paid for structural failure and human neglect. In the wake of such a tragedy, the imperative was clear: understand why. Forensic engineering teams descended upon the wreckage, meticulously collecting evidence, examining fractured components, and studying the surviving sections of the bridge. Every bent beam, every snapped rivet, every corroded plate held a piece of the puzzle. The goal was not merely to assign blame, but to extract crucial lessons from the disaster, to prevent such a catastrophic event from ever happening again. The investigation's findings were unequivocal. The collapse was not due to a sudden, singular event, but a culmination of years of insidious decay. Material fatigue, driven by constant loading cycles, had significantly weakened the bridge's steel structure. This deterioration was catastrophically accelerated by severe corrosion, a direct consequence of the aggressive marine environment and, crucially, a chronic lack of consistent maintenance. The very elements designed to hold the bridge together had been systematically undermined. The Faidherbe Bridge disaster stands as a chilling case study in the chain of errors that can lead to catastrophe. It wasn't just a material failure, it was a systemic failure. Warnings from engineers were downplayed or ignored. Necessary funds for maintenance were diverted. Short-term budgetary concerns overshadowed long-term structural integrity. This cascade of human decisions, combined with environmental forces, created the perfect storm, proving that even the most robust designs are only as resilient as their care. The lessons of Faidherbe, alongside other bridge collapses of the era, spurred a global re-evaluation of infrastructure management. Robust inspection protocols became paramount. No longer was it sufficient to merely visually inspect. Engineers developed sophisticated non-destructive testing methods to peer inside materials, detecting fatigue, cracks, and corrosion before they became critical. Thermal imaging, ultrasonic testing, and acoustic emission monitoring became standard tools, transforming reactive repair into proactive prevention. Beyond inspection, the disaster catalyzed advancements in materials science. Engineers sought stronger, more corrosion-resistant steels and innovative protective coatings. High-performance concretes, fiber-reinforced polymers, and smart materials capable of self-healing or signaling distress have revolutionized bridge construction. The understanding that bridges are living structures, constantly interacting with their environment, led to a new generation of materials designed not just for strength, but for resilience and longevity in the face of nature's relentless assault. Modern bridge design now heavily emphasizes redundancy. A single point of failure is no longer acceptable. Structures are engineered with multiple load paths, so if one component fails, others can take over, preventing catastrophic collapse. This principle, learned through bitter experience, ensures that bridges possess inherent resilience. It's an acknowledgement that perfection is unattainable, but catastrophic failure due to a single flaw is avoidable. Safety factors are larger, designs more robust, and vigilance a core tenet. Perhaps the most profound lesson from the Faidherbe Bridge collapse is the ethical imperative placed upon engineers and decision-makers. The responsibility for public safety is immense. It demands transparency, unwavering commitment to maintenance, and the courage to make difficult financial decisions that prioritize human life over cost savings. Engineering is not just about calculations and materials, it's about the moral contract we make with society, ensuring the structures we build serve, protect, and endure. The original Faidherbe Bridge, or at least its tragic central span, was ultimately replaced. A temporary Bailey bridge served for years, a practical solution to an immediate crisis. But in 2000, work began on a complete reconstruction, with a new bridge inaugurated in 2004. This modern Faidherbe Bridge stands today, a testament to resilience and learning. It incorporates the very lessons paid for with so many lives, blending historical aesthetic with contemporary safety and materials science. It is a bridge reborn, carrying the weight of both traffic and history. The story of the Faidherbe Bridge is not just a historical account of a disaster, it is a timeless warning. It underscores the critical importance of constant vigilance, of valuing proactive maintenance, and of heeding the subtle warnings that structures invariably give. Every bridge, every building, every piece of infrastructure tells a story of its own, if only we are willing to listen. The lessons etched into the fallen steel of Faidherbe continue to resonate, guiding engineers towards a safer, more resilient future, reminding us that the fight against decay and disaster is an eternal one.